Okay, yeah, so the topic of today, both days training really is our TrueView 3D IS training, mission planning and flight operations. We will be going out and flying 2 flights today, and we will process that data live in here. That will be the data set. Briefly, before I go into the product, it is kind of important for me to kind of go over our product ecosystem. We do have a large variety of products that sort of integrate to all of our products, and it's important to know them because I might make references to something like Reckon, and if you don't know what I'm talking about, it's going to be confusing. For most people's workflow, for the beginner, you know, really this bottom right sort of workflow is what you're going to use. You're going to use a sensor, and then you're going to post-process the data in TrueView EVO, and you're going to generate deliverables. And that's what we're going to be doing today. But we also have our cloud service, Reckon. It's hosted by Amazon AWS, and it provides a variety of different services like sensor subscription management. So we do have a subscription service for our sensors, and that's managed through there. Paid service metering, there's certain types of extra services that we offer that can be purchased with points and you know, bought piecemeal. Reckon also manages automatic diagnostics, so error logs from sensors when you process the data will be sent to the cloud server, and it gets parsed by software to tell us if there's any errors. So if you got some problem with your sensor, a lot of times we'll catch it early and we'll send you an email and be like, hey, something's up. You know, you need to do this, or you need to bring it in for servicing, or whatever. If you do work in a sensitive field, like federal government or research, we can turn that off. Just let us know. Calibration management is another feature. With calibration management, so there can be times where you need to get a sensor recalibrated, either because it's just been a while and your QCs aren't what they used to be, or the sensor's taken a bit of a bump and may have gotten uncalibrated. And when you have multiple calibrations, that sort of temporal aspect to that is managed in our services. So if you have a flight you processed last week with an old calibration, it'll pull the servers and pull that calibration instead. So it's just sort of an automatic way of managing calibrations for you. And then we also have paid services for data archiving and data presentation with Amazon Web Services. Okay, so this slide, I just kind of want to define some terms here so nobody's confused about things. You may notice we use this term 3D IS, which stands for a three-dimensional imaging sensor, and that goes for our LIDAR sensors. And the reason why we use that term is the data product that's derived from it. It's not really, you know, totally LIDAR or, you know, photogrammetry camera data anymore. It's been fused together into a colorized point cloud. And those products include our TrueView 500 series, 600 series, and now we also support DJI's L1 sensor. And then we also have options for PPK processing 2D imaging sensors, or photogrammetry only, and those are the ones that we currently support. The Phantom 4 RTK, we support the DJI M300 RTK, typically with a P1 camera. There are others, and there's likely to be more coming out. The DJI M210 RTK is an older model, typically with an X4S camera, and there's other types of cameras that may be supported. That's a very popular platform that's still has a lot of people out using it right now. All right, so the module content for today, we're going to go over a hardware overview of our TrueView LiDAR systems. We're going to go over the basics of mission planning for a TrueView 3D IS survey. We're going to go over TrueView flight planning with Litchi. The reason why I'm going to use Litchi is because it has a desktop application interface that's very visual and good for instruction. I like it as a flight controller, but certain types of drones, you know, you have to use the manufacturer's flight controller, so, or you might just have your own preference. So just remember that this is only as an example. We're going to go over field operations. We're going to go over field data checking, and then we're going to do post-processing LiDAR data and accuracy assessment. And like I said, the end game for today is colorized point cloud with an accuracy assessment. So that's where we're going to get to today. All right, module assumptions. This training module assumes that you are or work with an experienced, qualified UAV pilot, or already familiar with flying UAV platforms, preferably with experience on survey missions. have a background, a survey background, and are familiar with terms such as PPK and RTK and the basics of GNSS base operation. Training objectives. Upon the completion of the module, you'll be able to identify the key hardware components of a TrueView 3D IS system and demonstrate how to mount them to an aircraft, create a TrueView 3D IS mission plans and explain the trade-off required between altitude, scan angle, and airspeed to achieve the desired LIDAR and camera data results. Plan and execute a TrueView 3D IS flight in the field using Litchi, including the manual in-air initialization maneuvers. Okay. So here's kind of a basic components overview of our TrueView 515 or 435. They're form-wise, they're identical to each other. The only difference is the 435 has half as many internal sensors and cost a little less. So you can see up in the upper left-hand corner the Aplanix, which is a Trimble company, the APX15 POS, and that means something else. It doesn't mean that. It means a position and orientation system. And position and orientation system is just sort of a fancy term for a combination of a survey grade GNSS receiver with an IMU. So that means it's measuring X, Y, Z, pitch, roll, and yaw to a very, very high standard. The central board that runs all of our TrueView systems is a Google CPU, and we have our own custom system synchronization board to manage the master clock. This sensor is compatible. If you see at the top right here, we've got this dovetail mount. That's a Ronin compatible dovetail mount, but we've also adapted it to Grimsley mounts and other ones that are similar style. For the 515 and for our 600 units, we've got a new series out, but they are designed to have self-contained battery power. So that's a removable and replaceable battery that you can use for 2 to 3 flights depending upon the flight time. The good thing about having a self-contained battery is it makes integration easy with different drones because you don't have to tap into the drone's power supply and also kind of pull its power. The data management is handled through a USB stick, so it has configuration files that will that you can set options for the system, and it's also where the data is sent to that you'll grab and move to your workstation. This series of sensors is all mounted to a rigid aluminum frame, and that maintains the calibration and prevents any kind of flex. All TrueView systems have a dual 20 megapixel mechanical shutter cameras, and you can see they're angled about 25 degrees off port and starboard. And like I said, with the TrueView 515, it's got a 640 kilohertz with 2 returns LIDAR sensor, and then the 435 has about half that. They're a Hesai Pandar XT scanners. And here's the specifications for both of those sensors. The laser is a Class 1 905 nanometer laser, which is eye safe. The effective LIDAR range is about 80 meters. It's kind of a soft target though. You can go push it a little higher, but you'll start to experience a dropout. And if you have low reflectivity targets like fresh asphalt or a burnt forest floor, something that's a dark surface, that has less reflectivity and you might need to fly a little lower to get returns on stuff like that. So again, 80 meters is kind of a soft target. Cross-track field of view for the laser itself is set to 120 degrees. We do clip that a little lower during post-processing, but it is user adjustable. And like I stated earlier, the number of LIDAR beams for the 515 is 32 with 2 returns, half that for the 435. The accuracy that we rate the sensor at is better than 5 centimeters RMSE, root mean square error. It's sort of a standardized statistical method for measuring accuracy. The precision we rate to be better than 5 centimeters at 1 standard deviation or 1 sigma. Camera mounting, plus and minus 20 degrees, cross-track to get oblique photogrammetry. Kind of gone through, talked about the cameras. The lens, 28 millimeter, focal length of 2.8. It's a fixed focus. It is set to the focal length and the shutter speed are fixed, and the ISO is updated automatically for most applications, this is adequate for our surveys. The weight for these sensors with integration kit and batteries, 2.43 kilograms. That's below the payload limit for a DJI M300, which is a pretty popular aircraft right now. And then the weight, if you have used the external power adapters, 2.25. We rate the battery to be about slightly over an hour, which usually means about 2 full flights or 3 not quite full flights. All the ones that I just showed you all run the Regal Minivux 3 UAV, which is, I mean, you know, hands down, anybody will agree is the best LIDAR sensor on the market right now. It's expensive, but it's also the best. The effective range for these sensors, we rate them for 100 meters for targets above 20% reflectivity. And just like the last one, like I said, it's a soft target. You could nudge it up a little higher. If you have low reflectivity targets, you may need to fly a little lower. Cross-track field of view for the LiDAR scanner is the same. We set it to 120 degrees by default. The number of returns that you can get on one of these Regal sensors is 5. The pulse rate can be set to 100, 200, or 300 kilohertz. We set it to 300 kilohertz by default, and there's really no reason to go less than that, unless like you want smaller data by chance. And I think the 200 one's supposed to be like a power saving mode, but I think it's a pretty negligible difference. All right, so the difference between the 635, 645, and 640 and 50, as you can see, is the Planix APX15 versus the APX20. And you can see the different accuracy and precisions for those are you know, a little different and quite drastic from the 500 series. So, you know, at the highest end, you've got 2 centimeters accuracy and precision with a 640 or 650. So, you know, for UAV mapping platforms, that's the best you can get right now. Cameras are exactly the same, and here's the weight specifications on the bottom. Yeah, so you can see it's a little bit lighter, so it can mount on an M300. Sensor mounting, laser scanning cameras and position orientation system are all rigidly mounted to a connected aluminum frame, except for our new ones. That's not really aluminum frame anymore, so that only applies to the older sensors. And also, you can see on this, the laser scanner is also mounted such that the helicopter pitch pull to the beam makes it approximately nadir. So as the aircraft pitches forward, we design it with such a tilt that, as you can see from the graphic, it sort of makes the center of the beam nadir to your survey. Okay, TrueView integration with aircraft, and the picture above shows the 515 sensor in flight with a DJI M300 aircraft. TrueView integration, so the different kind of kits that we have for various aircraft is the DJI Ronin style dovetail mount, or sort of an alteration of a Grimsley mount. The DJI Ronin mounts, dovetail integration, let's see. The Grimsley one has built-in vibration dampeners with little silicone balls. The DJI Ronin mounts have those, you can see sort of those cylinders there that have springs in them for the shock absorption. The Ronins we use for the M600, which is now discontinued but is still widely in use. The Grimsley mounts are used for Inspired Flight 1200, BFDs, Watts, and Watts Prism. You can see on the bottom left corner image, this is an M600, and this is sort of an example of, you know, what an integration might be. This has a rigid mounting plate to where the TrueView antenna and the controller box can sit on for a stabilized platform. And every integration is different, but has some form of that. The integration can be done entirely by us if you do purchase a sensor and aircraft through us, and we're also open to custom installations. If you find some exotic aircraft that you fell in love with, you know, bring it by and we'll talk about integrating it, as long as it's a rotary wing, not a fixed wing. So here's some of the integrations that we have in use right now. We have customers actively flying integrations with these right now. Watts Prism, the Inspired Flight 1200. Let me just say too that the Watts Prism, Inspired Flight, the Alta, actually everything except the DJI is non-Chinese aircraft. So if you have clients that require, if you use defense or state contracts that require that you don't use Chinese aircraft, these are the other options that you have, and they are much more expensive. But some of them are pretty cool, like the Harris and the Skyfront are gas hybrid drones. So they can get hours worth of flight at a time. So it's pretty efficient if you're doing surveys that have very large areas. So installing the TrueView, at least with the dovetail portion of it right here, and we will see this when I physically bring in a sensor and aircraft. But the dovetail you can see in the upper left-hand photo just slides into that, and then there's a spring-loaded wing nut that you'll tighten down. And with these, actually that's not a wing nut, but it's. But you want to make sure to not ever over-torque these or completely unscrew them. If you over-torque them, you could strip out parts. If you completely loosen them up, it could fly out and the spring will eject. And if you're working in the field in a bunch of grass, that could ruin your day. So good to be mindful of that. All TrueView systems ship with a steel braided safety cable you can see in the bottom right-hand corner. So we typically loop that steel cable through the frame of the TrueView sensor and through the mounting kit of the drone itself. We've never seen one of these mounting kits fail, so it's purely a peace of mind thing. I already talked about the USB stick. The TrueView system's settings are stored internally, but can be changed by modifying the CoreConfiguration.json file that's located on the UMS. You may see me use this term UMS. That's sort of a term that the engineers put on me that stands for Universal Mass Storage. I don't know why we need that. I just call it a USB stick because that's what it is. But if you see that term kicked around, that's what it means. The system identifies if the file's been modified and then operates accordingly. Features can be turned on or off with true or false Boolean values in the core configuration file. Other fields can be configured with numeric values such as battery status, percentage, or proximity mode distance. We do recommend that if you modify text files, to do it in Notepad++. It's a sort of a programmer's text editor that has color coding and stuff, and it can save you from making syntax errors or typos. And I'll briefly go over some of these options with the core configuration file. Most people will never need to alter these unless you're sort of a power user or changing between different aircrafts. But one important example is the lever arm offset change. So every mapping drone platform that you see, whether it's ours, somebody else's, photogrammetry, LIDAR, something new that hasn't come out yet, you always need to know the distance between the center mass of your sensor and your GNSS antenna itself. It's important to know those values and for those values to be applied during processing. Otherwise, your positional data won't mean anything. And these values can be changed in this core configuration.json file. You can see we got them in here. We got the XY values in there. So if you ever need to change drones, you can punch those values into there and it will update them for you. There's also a guide in the manual for measuring your own lever arms. So if you're a do-it-yourself kind of person and you got a new drone, you can pull out a laser guide, some straight rules, and measure it yourself and put them in there. Or verify your own if you just want to be paranoid that stuff's in there and it's up to you. I'm not going to go into great detail with some of these advanced options, but I just do want to let you know that these kind of deep options exist for configuring your sensor. So you can see there's by default, the way that the cameras work on a TrueView is that both cameras have internal SD cards that are taking shots every 2 seconds and storing them to the SD card. When your data is finished and you've landed, it's going to transfer those images from the SD cards to the USB stick. And that can take a little bit of time. It can take, we estimate, about 5 minutes per 15 minutes of flight time. It's a lot of data to shuffle into the USB stick. Usually for most people that's not a problem, because between flights you kind of got to do the battery dance and field check your data, fire up your generator, do stuff like that. But if you have one of these extended flight drones like the gas-powered Harris and Skyfront, you might be flying for 3 hours before you land. So having this automatic image transfer is not a good thing at that point. And you have the option in here to turn that off, and you can retrieve the images later manually if that's the workflow that you want. There's also options in there for manually changing the camera settings. So like I said, the focal length and shutter speed are set fixed, and the ISO is adjusted for the exposure mid-flight. Those settings have worked good for years for all of our customers. Obviously, if you're trying to derive a orthomosaic from your data set, having overexposed, underexposed, blurry images, anything like that will affect the quality of your orthomosaic. We do have options in here for changing like the field of view or pulse repetition rate for different sensors in there. It's something almost nobody should need to do, but they're in there if you need them. Here's more of those kind of options. But to get on to some more general or important options, the battery percentage for this controller box. So you can see in the bottom right-hand image, we've got this device called the controller box. And in most integrations, it sits on top of the drone, so you don't have to, crawl around on the ground like an animal looking at, lights and codes and stuff. You can just stand there and see it, and it's actually bright enough where you can peripherally see it out of the corner of your eye while you're doing field operations like shuffling your batteries around. But the important thing about this box is that it has 3 light codes for battery, GNSS, and system, and there'll be a variety of different colors and codes that will let you know the status of your system, the battery being the most important one. By default, it'll be green if you're above 50%, it will be yellow if you're between 50 and 30, and it'll go red if you're below 30%. So at a very quick glance, you can know what your battery position is, or battery status is, unless you have a integrated power module. These thresholds can be changed there in the text file if you need to. And another important feature that needs to drive home with the system is what we call proximity mode. So the default behavior of a TrueView system is that when you boot it up and it's ready for flight and data collection, as soon as you take off and you leave a 25-meter sort of 3-dimensional bubble, it will initialize data recording. So you go up 25 meters, boom, it starts recording. And the exact opposite happens when you land. Once you come back into that 25-meter bubble, it's going to start winding down the data cycle. Yeah, and the exact opposite happens with proximity mode. As soon as you come into it, it's going to wind down the cycle. Usually when you walk up to the aircraft after it's turned off, you'll look at this controller box and it'll say downloading data. It's already starting to do the work for you as you're walking up. And again, within this, the CCF or the core configuration file, you can change these options if you want to. You can completely disable proximity mode, or you can change that 25-meter range to something else. There's been a few cases where this could be a problem for certain people. I knew somebody who had to fly like a 15-meter high flight one time because of flight restrictions, and they set up in the middle of their site, and as soon as the drone came near them, it started to wind down in the middle of the survey, and they lost that data. So it's important to be aware of those values. Another important option with controlling the sensor is the AutoDelete feature. So for the SD cards and the USB stick itself, if the capacity of the storage medium gets up to 80%, it will delete all old data until it reaches down to 20%. So it does that so you don't run out of storage mid-flight and lose data. But obviously, if you hadn't been backing up your older data, you could lose it. So it can work against you too if you're not backing up your data regularly. And just like every other option, you can disable this or change the values. So you can turn it off, or you can change the threshold to 90% and 50% or whatever you like. So the lighting codes for that controller box are pretty important, and we have in the hardware manual for the TrueView system, we have a exhaustive table of all these lighting codes that, you should, I would recommend, always bringing a manual to the field with you, whether it's printed or just a PDF on your phone, so you have reference to these kind of codes or other troubleshooting things. If you ever see a red light and your battery's not about to die, that's probably a bad thing, this is just an excerpt of that table, and you can see, like, if you've got a solid red light on your GNSS, that means that at some point during the survey, you completely lost GNSS connection, which is the worst thing that can happen other than crashing, because you don't have good data. So you need to investigate why that happened and most likely refly your mission. If it's blinking red, that means you drop down to 4 satellites, which is effectively just as bad. So I highly recommend to all operators in the field that you monitor these light codes and look for these problems, because that's kind of your first line of defense for field checking your data. And field checking data is a very important topic that I'll go over exhaustively later today in another slide. Field operation before flight. Obviously, this does pertain to if you're using a battery pack. And so to power on the system, you'll want to open up the battery component. You can see that there's a toggle switch in there. For the 500 series, the switch is above the battery. For the 600, it's below it. Then you'll want to close the battery compartment. And then after you do that, all of the lights on the controller box will start flashing yellow. And that's when it's booting up the system and initializing. And then it's going to go through a whole series of booting. Like, the first thing it's going to do is check the battery status and let you know that. It's going to start acquiring satellites for the GNSS signal and let you know what the status of that is. You do want the GNSS to go green, which means it's got enough satellites for a fix. If it's less than that, you might be in a bad position. If you're setting up around vertical obstructions like tall buildings and trees, that can obstruct your GNSS signal. Or also interference can be a problem if you're setting up around radio and communication towers, or other sources of interference like power substations. You got to always be mindful of your launch position, because you want to start off with a good GNSS signal. Once you actually get up in the air and away from obstructions, it's less of an issue. All right, so as it initializes the system components like the LIDAR itself and the cameras, the system light will flash yellow, and then it will turn solid green. And then when it gets ready for proximity mode, it will be blinking green. So most common operations, you'll look for the lighting code like green, green, blinking green. And you can actually see there's a LCD readout on there, and it'll give you a text readout of what's going on. So it'll say proximity mode ready. And if you do want to disable proximity mode, that big green cycle button is how you can manually start and stop data cycles. So if you disable proximity mode, you can just hold that cycle button for about 5 seconds, I think it is, and it'll say data recording started. You can take off and execute your mission. When it lands, you hold it again for 5 seconds, and it will say data winding down, and it'll start to close down your data set. After you've hit that button or initialize proximity mode, you'll want to take off and climb to a safe altitude, and then you're going to want to perform the heading alignment maneuver, which is sort of a calibration maneuver that will help calibrate the position and orientation system, or more specifically the accelerometer that's inside of the position and orientation system. And then you'll want to execute your planned mission. All right, so the heading alignment maneuver, or the HAM, is performed twice. You want to do this after takeoff and before the mission starts, and then you want to perform it after the mission is completed and before you land. And you can sort of see there's a visualization in there showing how that works. The way that you'll do this heading alignment maneuver is you'll just push the stick forward, as fast as you can to accelerate to 10 meters per second. And then once you've seen your aircraft hit about 10 meters per second, you'll let go of the stick and let it stop and settle for about 2 seconds. And then what you want to do is you want to rotate the aircraft about 10 degrees and do the same thing backwards. Pull back full speed until it reaches 10 meters per second. This 10-degree rotation, this isn't actually required for the heading alignment maneuver. It's more of a safety thing, because if you're going forward with your aircraft, you don't want it to come backwards directly at your person, you know, for safety reasons. So just good to know that. And the heading alignment maneuver is basically what it does is it aligns the accelerometer on the IMU, and what that does is it minimizes a heading drift. So, you know, when you're flying, the accelerometer is what tracks your yaw, or the direction that you're traveling. And just by the nature of the way accelerometers work, the more they stay on a steady course, they start to experience drift. So doing this heading alignment maneuver will minimize that. Field operations after landing. So you'll want to stop the mission on your flight controller software. You want to fly back to the home point but not land. You're going to perform that heading alignment maneuver and land, and then if proximity mode's active, the aircraft lands and wind down will begin. Okay, so when you land, again, if you have proximity mode, it'll already start winding down, or you'll need to press the button to manually initialize the wind down. Very important to not power off the system while it's doing this. Obviously, that'll interrupt it downloading its data and organizing the data structure into something that you'll, you know, post-process on your workstation. Our firmware does have a lot of safeguards for cycle recovery if that were to be the case. If you just accidentally shut it off because you're in a hurry, I've done that many times, or your battery dies. I have another slide here in a little later that will talk about cycle recovery if you lose a data set or because of a premature power down. In most cases, the data is recoverable. You just kind of have to go through a bit of a few steps to get it. The major things that it does when it winds down a cycle is, the first thing you'll see it do is it'll say downloading TO4 file, which is the rover file from the Planix. And that's usually like 20 or 30 megabytes, pretty small, but very important file. And then after that, it'll start doing the camera wind down. That's the most time intensive one. And it'll give you a percentage. It'll say, you know, downloading camera images, 32%, blah, blah, blah. So you'll know where you stand. And usually what I do is I'm swapping batteries and at my work truck and just peripherally watching the lights, you know, and when I see it go solid, I know it's done. And cycle recovery. This slide's a little bit too wordy, but if you're seeing a message on your controller box that says hard error, there are ways to investigate after turning the system off. If you plan to submit a support case or investigate personally, perform the following steps. Go ahead and power off the TrueView, turn the TrueView system back on, and wait for it to say copying old files. That's the message that you'll see when it's trying to recover a data set from a hard fault or a premature power down. One thing to be mindful of with the TrueView systems is the image write time and data formatting. So, you know, the SD cards that go into the cameras and the USB stick, they're just like any sort of other computer medium. You know, if they haven't been formatted in a long time, they're eventually the file systems will get kind of gunked up and have less and less performance over time. So we can't set a certain, you know, metric on how long you need to do data formatting, because everybody's volume of work is different. You know, some people are out there doing multiple surveys a day, some only do once a month. But periodically, you do want to format your mediums to keep them running efficiently. And I'll go into the basics of planning a TrueView LIDAR mission. So this is an M300 already set up with a 515 sensor. So I'm actually I'll break this apart and put it back together for you just to kind of see all the components and kind of see how they all work together. So you can see this is the braided steel safety cable, and it's looped through this aluminum frame and through that Grimsley mount right there. So I'm going to go ahead and just take this off real quick. All right, and then you can also see we've got two cable connections right here. So this one right here is a coaxial cable. I'll screw this off, and this goes to the GNSS antenna right here. So I'm going to pull that out. And this right here is a Cat6 network cable that sends and receives data from the controller box up here. And one good thing about this cable is if it ever gets nicked by a propeller blade or has any kind of fault, you know, you can probably go to Best Buy or something and just get a quick replacement cable. So that can save your hide in the field if it ever gets damaged in some kind of way. So these are coming up to these components mounted up here at the top. I'm going to take these off and kind of explain them. So this right here is the antenna mast, the GNSS antenna mast, and this is the GNSS antenna. So when you break apart your system and reassemble it, you can see that there's a coaxial port right there that you can put and screw back on. It does have this we have this sort of squishy material, slightly squishy material right here. And the reason why this is here is to just have it a little bit of give. So if you do tighten down the threads on this a little bit, you're not stripping the threads. It's got a little bit of squishiness to handle that with. This sort of aluminum disc that you got around here, this is really just to prevent multipathing from the top of the aircraft. So if you've got signals coming from GNSS satellites, they could ping off this and cause multipathing error. So it's a pretty marginal increase in data quality, but it does count. I've seen a lot of people that have this bent for some reason, and they freak out and they're just like, "We need a new one, it's bent." And I'm just like, just calm down, just get some pliers and straighten it out. It's not going to largely affect your data. Now this GNSS antenna right here, you'll see that we've got this part right here. This is the GNSS antenna mast base that it clicks into. And it's actually got one of those little ball bearing things that click into it. And obviously you want to always make sure that you push this all the way down, because the offsets for the GNSS antenna are measured with this in mind. So if it's sticking out halfway, you're going to introduce vertical error, and it also might make it a little wobbly and fall off. So always important to push that all the way down. Now this controller box right here, this part right here is called the controller box mounting plate. The mounting plate and the GNSS antenna base mast, these can remain on and go into the storage case. Usually I got to route out a little bit of the styrofoam right there to fit it into the case, but this can just stay on there. So these are the parts that are removable. And you can see the controller box has 4 little legs there, and they've got little squishy insert things that they'll push down and clamp into right there. So that's those components. Okay. And then let me take this TrueView system off and show you that. You can see on the side there, it's got the USB stick just kind of hanging off on the side, plugged in right there. And if it makes you feel better, you could attach a lanyard to it, or you could even thread the safety cable through the little hole in it and secure it that way if it makes you feel good. Okay, so for this is a really kind of hard thing to see, both for the cameras and personally, but see that little red nut in there? That's part of the dovetail mount. So I'm just going to come down here and probably unscrew it, I don't know, 2 or 3 times is about all it takes to loosen it up. And then the dovetail can come out either side. Take this USB stick off. Yeah. So there is the physical TrueView system, just like the slides show. LIDAR sensor, cameras 25 degrees off the sides. There's little rubber bumpers right here, or little rubber stoppers that the SD cards are held into. Here's where the battery goes into right there. The power adapters for aircraft also have the same form factor. They'll just plug into that and connect to the power and then connect to the aircraft itself. There's the toggle switch in there. This also has a, because it has a little computer in it, it also has a ventilation system. So you can see there's a intake fan with a little dust filter. So you'll periodically want to pop this out and blow it out with some air. Yeah, there's another ventilation port right there. I can't remember off the top of my head which one's the intake and the outtake. Another important consideration to remember, especially if you're using this 515, is this serial cable on the side here. This is what's called a LEMO serial connector. And in most cases, this will never need to be removed, but it's just good to know that that's a troubleshooting step if you're ever having problems, to make sure that hasn't been removed or damaged by any way. I've had some people try remove it and try to forcibly put it in there and twist it and break the pins off, and that'll obviously cause the whole thing to malfunction. So just good to know what that is and to be mindful of it. So we'll go ahead and put this battery back in, and then I'll just sort of assemble this together, which will, you'll see, which is, basically the same process that you would go, you would start a field day as you pull your drone out, set up everything as is, mount these components, and then come in here and mount the LIDAR. It's important to remember with all TrueView systems, the battery or power facing part always goes forward with the aircraft. That's the way it's designed to operate. Battery forward, LIDAR to the back. So I'm gonna put that in there. And usually what I do with these dovetail mounts is I kind of run my finger down the side of the dovetail mount just to make sure it's flush, at least sideways. And then I usually kind of like prop it up from the bottom a little bit just to make sure that it's not screwing in there crooked, and give that a twist. And make sure that the nut on there is just snug. So that's mounted, and I can connect the controller box cable and the coaxial cable for the GNSS signal. And then I'm going to put in the USB stick, and just to note that we ship these with, you can see it's kind of a dual-sided one. So there's a USB-C side right there, and then a USB-A side right there. So the C side goes into the TrueView, and for workstations, if you got a C, obviously that's going to have higher throughput, or an A if that's all you've got. So I'm just going to plug that in. And one thing to keep in mind too about USB-C is it's a reversible connection, so you don't have to worry about which direction it's going in. And I think I'm going to follow my own advice and just thread this safety cable through that USB stick. So I'm going to go under the aluminum frame, through this zip tie here, over the integration kit. Actually, I'm going to go through just a single arm of this aluminum frame. All right, so that's that. Yeah, with the USB stick, the requirements are USB-C, and it needs to be formatted in exFAT format, and then it needs to have our 2 configuration files on there. So there's a CoreConfiguration.json and a SystemConfiguration.json, which is the calibration for the sensor. So, I recommend to everybody to have at least one backup. That way, if you fill one up, you go ahead and swap it out, or if you lose one or one malfunctions, USB sticks are not expensive. Get 2 or 3 and keep backups. So, but yeah, that's the system assembled. You can pretty much see, like, you can hop out of your truck and have this thing thrown together and ready to fly in 20 minutes, aside from your base station operation and checkpoints and all the other field requirements. But this itself, you can set up pretty quickly. Okay, so the next section that we'll go over basics of planning a TrueView LiDAR mission. So we'll cover the way that flight parameters can affect your data, a very important topic, and then also I'll do a demonstration of flight planning for Litchi. So I'll actually plan the flight that we'll do today, and then once we get done with this section, we'll head outside and do 2 flights and come back in and process the data. And the reason why I'm going to do 2 flights is because we have a workflow where you can import and process multiple flights into one project. So most people do that. So it's a very important workflow to be familiar with. Okay, so camera. So TrueView 3D IS includes two 20 megapixel oblique mounted custom mapping cameras, fixed focal length mechanical shutter with MEP signal, which is a mid-exposure pulse. That basically sends a timing. So right when the camera's mid-exposure, it sends a signal to the Aplanix APX15 or the POS to record that time. So that's how it's that's how the cameras are sort of geo-positioned by the timing. They're oblique cameras, so they cover a full 120-degree swath width, and they're auto-triggered every 2 seconds. So when you're doing flight planning, the equation that you want to solve for is really what's my line spacing, and then you kind of work backwards from that. So line spacing is the distance between flight lines. That's the 70-meter spacing that you can see on there. I know this graphic's a little crude, but you can imagine that the top of that pyramid, sort of the sensor origin, and you can see that by default, the sensor field of view, at least the way that we clip it in the software, is going to be 40 degrees positive and negative off the side of it. And then you can see we've got flying height, side lap, and swath width. We'll get into those in just a minute. But we're going to talk about line spacing now. So line spacing should always be carefully planned to avoid data gaps. The number depends upon the combination of the other factors. So every parameter alters the other one. If you fly higher, your swath width gets larger, your flight line spacing gets more narrow, so on and so forth. If your scan angle opens up more, your swath width's wider and your line spacing can be more narrow. All right. So flying height should not exceed the maximum range of the LIDAR or dropouts could occur. So like I said earlier, with the 500 series, that's about 80 meters. With the 600, that's about 100 meters. And another consideration with that too is just because you can fly that high doesn't mean you always necessarily want to. You're going to get, the lower that you fly, the more returns that you're going to get, just because the more energy it gets to the ground. So that's always a balance to consider with LIDAR missions. Lower altitude means a more narrow swath and less coverage, and there's the altitudes for those sensors. The scan angle is the angle off nadir at which the LIDAR will be clipped. Again, this can be changed in post-processing. What it's actually collecting by default is actually 60 degrees plus and minus off those sides, and we clip it down to 40. So you always have that option later in post-processing to widen it out if you need to compensate for shadowing or gaps in your data set. Larger scan angle produces larger swath widths, but can create bad incident angles at the swath's edge. So the further you get to the edge of your swath, the more the less accuracy that you're gonna get. It's marginal, but it's there. So that's why we recommend the 40 degrees by default. All right, and side lap. Side lap, I'm sure a lot of you are familiar with photogrammetry and how important side lap can be. Generally in photogrammetry, you want your side lap to be 60% or more to make tie points for the photogrammetric software. But with a LIDAR sensor, it's got a totally different purpose. For one, with the cameras themselves, you don't have to worry about the side lap so much because it's always kind of overshot because you've got a 120-degree field of view because of the oblique cameras. The side lap consideration is more for the LIDAR itself. So the area between the two flight lines where the LIDAR overlaps is what we call the side lap. This can be used for a flight line alignment analysis. So if you think you've got any kind of data quality issues with your survey, you can pull up a profile and look at the way the side laps run into each other. If they blend very well, and we'll see this, I'll show some data examples later, but if they blend very well, you've got good vertical integration of your flight lines. If they kind of have like a sandwich appearance, like stacks of paper on top of each other, then you've got some kind of flight line misalignment. So you always want to kind of inspect for that and make sure you don't have those problems. And if you do, we have tools for correcting that. TrueView EVO now ships with a tool called Strip-Align, which can fix that. And there's also other point cloud tools. We sell TerraScan and TerraMatch that can do those. But it's a pretty rare occurrence. But if you ever do have a data set that's less than optimal quality, it's always good to have the options to fix it rather than have to go back out and refly it. The side lap also provides a margin of error if terrain elevation varies. So if you've got like a little landform or something, and it could cause shadowing, like one of your flight lines gets blocked by a bump in a landform, and there's lack of points on the other side. Having that side lap can fill in for those. Also, changing your scan angle can do that too if you ever experience shadowing. Side lap can also be used to increase the point density. So if you plan your mission to have 50% side lap, you're going to be getting double density data, at least on the interior overlap portions of your flight. So that's just one strategy. If you've got a very dense canopy that you're trying to penetrate, like if it's the peak of summer and you've got kudzu and privet and just crap all in there that you're trying to get through, doing the 50% side lap can be one of the strategies for doing that. Another one too can be doing sort of a crosshatch flying pattern, which we'll actually do today. So we'll fly one flight that's north-south flight lines and one that's east-west flight lines. So that'll cause double density data because we're surveying the same area twice, and it's also hitting through that canopy at different angles. So you're getting more opportunities to get penetration to the ground. And if any of y'all aren't very familiar with LIDAR, a lot of people will kind of erroneously say that it can like see through vegetation and stuff. That's not true. It just does it by brute force. Like you fly over a forest and you just hit it with millions upon millions of points. You only need a few of those to get through to really make a good, topographic map of something. But LIDAR also does have multiple returns. So when you look at sort of a vertical plot of the energy returns from the LIDAR, you'll see spikes in it, and those spikes will be coded as multiple returns. So as it penetrates through a canopy or really any vertical surface or vertical feature, it'll have multiple returns. So you'll see all the details of the leaves and the trees and the power lines and complex vertical features like that. Let's see. Data holidays. This is sort of with flight planning, this is a topic that needs to be considered if modeling vertical features is your application. Most people just want the ground. That's 90% of the applications. They want a topographic survey. But we do have customers who work for like the U.S. Forest Service and are trying to extract canopy height models, or we have customers who contract to electrical companies that want to map their power lines. So they can map power lines and measure sag or inspect power infrastructure on the poles. So there's a lot of different applications for LIDAR. But when you do have a vertical feature, you want to make sure that the combination of your swath width, flying altitude, scan angle, and flight lines are such that you model those features. You can see in that example right there between the, we're sort of looking parallel to a flight line. So you can see the gray tops are the sensor origins, and we're kind of looking straight down a flight line, and the different colors are the different coded by different flight lines. And you can sort of see that upside down triangular void there in the tree canopy. So no points were recorded there. You don't have anything there. If this was a data set that a forestry person wanted, this wouldn't be good for them, But if you're trying to get topographic survey, it doesn't matter. You're trying to get rid of the forest anyway. Same thing with buildings and stuff. If there happened to be a multi-story building right there in that triangle, it wouldn't get totally scanned. To get past this, you'll notice I got this screenshot here. We have a pretty elaborate flight planning spreadsheet where you can punch in values and formulas will be updated to tell you how to update your flight parameters. And one of those tabs on the spreadsheet is the vertical surface formula. So you can put in the V value for the vertical surface you're trying to get, and it will tell you the maximum amounts that you can do to manage that. So data holidays, always good to keep that in mind. Recommended approach, decide upon the field of view that you're going to use or scan angle. Again, 40 degrees plus or minus is our default. And then what you're going to want to do is you're going to open the flight planning spreadsheet and calculate or look up the values that will fit that FOV. Decide on the amount of side lap that you want, and then plan the mission for that. So This is a screenshot of the lookup tables that we have on the spreadsheet. I'll open the spreadsheet in a minute and show it to you, and also show you where to get it. So the way this works is you can see there's a value up there that says 25%. That's going to be the side lap that you want. You'll put that in there and then look up on the left side of the table. I'm looking at the bottom table here. Look up the scan angle that you want so you can see highlighted. We have 40 degrees by default, and then we'll look at the altitude on the top of the table, 60 meters in this example, and this tells us that we want our flight line spacing to be 75 meters. And there's also a point density calculator on there too. So some clients may have point density requirements, especially federal or state agencies will say you have to have 200 points per square meter or some requirement like that. So if you just want to check and make sure that you're meeting those requirements or your own, you can punch in your flight parameters here, and it will update and give you, you can see I will get this average point density on a single pass, like 282 points per square meter on that. And let me go ahead, I'll show you that spreadsheet. Yeah, so here's the spreadsheet. You can see we got all kinds of tabs down here with all this cool stuff in it. For most people, this first page right here and the second table at the bottom is what you're gonna want. So you can see I put in like 30 for mine, and let's just say we wanted to do 50% side lap for the double density data. If I punch that in, you'll see all the values are updated. It's all coded in there with formulas and stuff, and you'll just look up what you need and decide what you want. I won't go into huge detail with all the features on this spreadsheet, but there is an option on here to estimate your GSD for your orthomosaic ground sample distance, basically your raster cell size or resolution of the image that will be produced. You can kind of get an estimate for that. And I do say estimate because the nature of the cameras being oblique, like pixels on the far edge of the scan angle are gonna be larger, I think, than the ones towards nadir because it's oblique. It's not a nadir camera. And here's the point density calculator for the 500 series, 600 series. We had an older 410 series, which it's still a lot of them out, but I don't think we sell anymore. Here's with the vertical surface for the data holidays thing I mentioned. Here's the spreadsheet for that, and there's also some conversion formulas in here. You can get this spreadsheet, and if and when we do update it, updated versions of it are available on Reckon. So I hope all of y'all got the Reckon login credentials that I sent y'all for the email. You can go in there and just go to downloads, notices, and it will have manuals, spreadsheets, all those kind of materials that you need like that. This is also on the FTP link too, if you have that. So I'll go ahead and close that. And that's just some trigonometry if that's your thing. And then just some common settings. These are just very, very generalized settings. But for example, if you had a thick canopy, you might want to fly lower. You could do 50% side lap, cross hatching, and you can also fly lower to try to get more energy to the ground. If you're going for max coverage, so if you've got a huge open area and you're trying to suck up as much data as you can faster, you could open up your scan angle more, fly as high as your sensor can handle, and get the largest swaths you can. So with flight planning, it's always a balance between data quality and data efficiency. So you got to make those calls per project. Okay. Preventing heading drift. So I kind of already touched upon this with the heading alignment maneuver. And again, this is caused just by the nature of accelerometers drifting over time. All flight plans should utilize a straight or box turns to improve the IMU outputs. This creates a heading change and creates acceleration and deceleration. So you can kind of see in this image, I came to waypoint 2, and the flight controller, in Litchi's case, and DJI's flight controllers at least, when it comes to that waypoint, it's going to come to a complete stop, turn 90 degrees, accelerate to the next waypoint, come to a complete stop, turn, and then resume that flight line. So just that instance of having 2 hard stops with an acceleration in the middle is sort of another initialization maneuver. But one thing to keep in mind with that, the flight line limit should be 500 meters if you have a system with an APX 15 in it. If you have one with an APX 20, it can be 6 kilometers. So 500 meters is about the point where the heading drift starts to get a little too high for our comfort, and that's what we recommend you chop the flight lines off. So you can see in this one, these Flight 1 and Flight 2, these flight lines are about 500 meters. So we just kind of took this project and chopped it in half into 2 flight lines and kept them at 500 meters. That's one tactic that you can use to do this. Another one that you can do is you can actually add a heading alignment maneuver in the middle of it. So in this example, we're kind of doing this little triangular maneuver. Like you'll come up here to, you can see it goes from waypoint 1 to 2. It stops, turns 90 degrees, juts out a little bit, and then it returns back slightly before its stop point, and then continues on there. So if you have a really long flight lines, and sometimes you don't have a choice, you have a linear corridor type survey that's roads, rivers, stuff like that, this would be the tactic that you would use on that. You would do these every 500 meters, or 6 kilometers if you have an APX 20. And this chart kind of illustrates, why that's needed. So the chart above is this is a data from a real flight, and the top chart is the heading in degrees, and on the bottom chart, the blue line is tracking the heading error for an APX 15, and the orange line is the APX 20. So just look at this first flight line. You can see as gradually as we're going along it, you can see that heading error goes from about 0.1 to about negative 0.4. But you can see that the APX 20 is far, far less than that. And then once it reaches the end of that flight line and makes a turn, it resets and then creeps up again, and so on and so forth. Does that make sense to everybody? I know it's kind of some nerdy, math stuff.
Is the data collection paused during the alignment maneuvers?
No, it's not. It's still going. But that will be clipped out during post-processing. So one of the things that we'll do when we post-process today is these interior turns, also your takeoff and landing, the heading alignment maneuver, all that sort of extra stuff that we don't want to consider data, that'll all be stripped out, and that'll improve the accuracy of your data to remove all that, cutting off the fat basically, and it'll also make it more efficient because you'll, trim off all that stuff. Okay, so I'm going to jump over into Litchi now and kind of show you how this works, and sort of this is the end goal. I think this is one of the training sessions I did a few months ago, and you can see the aerial map is where we're making the building here. It's still in progress, but you can see we did sort of almost east-west and north-south flight lines on there. So I'm going to go ahead and jump over into Litchi. And if you have a Litchi account or want to create one real quick, you could follow along with this if you feel like it. Litchi is it's a paid app on the the Apple or the Android store. But to just you can make a free account and kind of poke around with flight planning on here for free, just to kind of get used to it. So this is Litchi. It's got a web interface here on the web browser, and Litchi's my personal favorite for flight planning software because one major feature is that you can import and export flights. So you can make a flight, and if you've got a coworker and be like, hey, here's the flight, they can import it and work with it. Or you could trade it with clients and stuff. DJI tries to lock that down. They want you to buy a cloud account and do all this goofy stuff. Yeah, and like Eddie said, that's really the key feature with Litchi is it has terrain following. So the way that works is Litchi will pull elevation data from the USGS's digital elevation models, and when you plan a flight, it will contour the terrain. So you can say, I want to fly 30 meters above the terrain. And if you have a mountain that's 30 meters high, you know, instead of running into it, it'll contour it. And that's good not just for safety, but also for data quality, because the lower you are, the more energy you get to the ground, you know. If you're flying 30 meters from the ground and you've got a dip that goes down, you know, 100 meters, you're gonna have a hole in your data down there because your drone didn't go down there with it. So data quality and safety. There are other flight controller softwares that have terrain following, and a lot of other drone manufacturers have terrain following built in. They'll actually have a very simple laser mounted on the aircraft that'll constantly shoot down and measure what its distance to the surface below it is. That's not exactly you know, elevation tracking, but it's something. All right, so on this, you know, what I want to do to start making waypoints is I can just left-click anywhere in here and start dropping waypoints and planning this out. But before I do that, I'm just going to check some settings real quick. There are some very important settings in here, most notably the heading mode. So I think that by default, if you have a new account, it will start with initial heading mode. And this may apply to other flight controller software too. I'm not familiar with everything. But the reason why you want to put the heading mode on auto is because the aircraft will always face towards the next waypoint. If it's on initial settings, it will like fly to a waypoint, crab walk to the next, and then fly backwards to the next one. So you'll be going in all kinds of crazy directions, and you don't want that. So you want your heading mode on auto. Finish action, set that to whatever you want. Return to home, or just none. It'll just pause once it's finished. Pathing mode, you definitely want straight lines for the reasons I just outlined with the heading alignment maneuver. You don't want curved turns. And then the cruising speed and max flight speed are exactly what they sound like. This is where you just put in the default speed. For TrueView missions, we recommend doing 5 meters per second. You can go up and down a little if you want. You know, if you slow down from 5 meters to 4 meters per second, you're going to get more dense data. That's another way that you can, you know, handle canopy penetration. You know, if you want to go to the Yucatan or something and you know, penetrate that thickness, you might slow down to 3 meters per second, do a crosshatch pattern, and 50%, you know, side lap. You know, you can go crazy with it. So just on this, I got it set to 18 kilometers per hour. That roughly translates to about 5 meters per second. If you are going to use the elevation following feature, you'll want to click this Use Online Elevation. This is the option that will pull elevation data from the USGS. There is an option to load your own DEM data if that's something that you're interested in. So now that those options look good, I think what I'm going to do is I'm going to come over here and let's see. I'm going to start a waypoint right there. And I'm going to put in the altitude that I want. I'm just going to, we'll do 60 today. 60 is a good middle point, you know, for most flights. You go up all the way for more data efficiency, down for canopy penetration, but 60 is about the good midpoint. The speed is auto-handled. We already put that in. And now I'm just going to come over and drop another one. And you can see it's got the elevation written there on the waypoint. And I'm going to be sure not to cross this road because we are currently in a Class C airspace. So the maximum ceiling height on this side of the road is about 75 meters. If I go across the road, I think it might be 0. I don't think I can cross the road. But I did a flight authorization earlier. So it's, you know, it's good to always be mindful of your airspace and get authorizations if you need it. So there's waypoint 1 and 2. And if you remember back from this spreadsheet, let's just think about what we're going to do here today. I'm going to do 30% side lap. I will use the default 40-degree scan angle, and we will fly at 60 meters elevation. So my flight line spacing needs to be no greater than 70.5 meters. So when I come back over here to Litchi, I'm going to add this turn, and you can see as I drag this waypoint, it's got the value in there. So I'm just going to kind of get it ballparked to 70 meters like that. And then come over here, and try to make this parallel to this one. And you can kind of see with Litchi and other flight planning software, like this isn't, this isn't some like highly accurate, CAD CAD stuff, or it's just kind of being visually placed like this. But if you want to be surgical with it, you could create a flight line in GIS or CAD or something, or even Google Earth, and import it into here if that's something that you want to do. So I'm going to come down here and make another one. And finish that line. So that's 3 flight lines right there. And if this is all we're going to do, what we generally recommend for for most applications, you don't have to do this cross-hatching thing that I'm going to do. This would suffice for very, very many applications. And when you do this, one thing that you're going to want to do is always add a perpendicular flight line across a hard surface for analysis and quality control. So in this case, I'm going to come over here, and then I'm just going to go over the building like this. And what that will do is later, once we processed our point cloud, we can draw profiles across the rooftop and examine the vertical separation of the flight lines and see if we have any data quality issues. Or we could use that parallel flight line to do data alignment with. But we're not going to do that for this one. I'm going to go ahead and do cross-hatching flight lines. So I'm going to come over here and do a north-south one like this. Come over here and do 70 meters again, roughly. And I'm doing the exact same thing. You can also see I've got the distance in flight line and estimated flight time up there. So that's a good way to track how many flights you're going to need to do for your project. All right, so there's that. And you might notice that this flight line didn't totally get over there to the eastern boundary of this. I've probably still got a good 20-meter gap right here. But if I go back to my spreadsheet, you can notice that if I'm flying at 40 degree scan angle, 60 degree scan height, my swath width is about 100 meters. So that's 50 meters on each side of the aircraft. So even though I've got a 20-meter gap here, I'm still covered. So good to keep that in mind. So that's the flight plan that we're going to do today. It's only 8 minutes, very short flight. I am going to break it into 2 flights, though, just for a training example. So I'm going to fly the east-west ones, land, go through the wind-down process and show you how that works, and then we'll take it back up again, repeat the process, and then when we process this data set, we'll merge the flights together into a single point cloud and that'll be our working data set for the next 2 days. I'm going to go ahead and save this mission, so I'm going to go over here to missions and save, and I will call this Triana Training. What is it now? The 16th, March 2020, 60 meter AGL, like that, and save it. And then you can also see in this missions thing right here, here's where we can import flights, export it as a CSV, or export it as a KML to send to other people. To open this flight in the flight controller software, I'm going to be using a tablet, external tablet, to control this aircraft. And I'll open the Litchi app, and if you have internet connection, you can use the Litchi app to download any of these flights. And if you go into an offline situation, it does cache those flights, so you'll have them there for you. So, got that saved. Yeah, I think everything's good. Okay, so flight operations. Flight operations for TrueView 3D IS surveys must follow standard best practices and safety requirements for commercial UAV operations. All local and regional flight requirements and airspace regulations must be adhered to. Any specific regulations related to the use of a LIDAR system on a UAV must be followed. All TrueView 3D IS systems have a iSafe Class 1 LIDAR system. Base station requirements. This is an incredibly important topic. So the TrueView uses a PPK, or post-process kinematic solution. So GNSS signals must be recorded for the duration of the flights. You got three options for having a base station. A local base station, which is, we highly recommend be the practice for everybody. That's when you have your, physically have your own GNSS base station that you set up and operate during the duration of the flights. You can use a core station, or if you don't know what that is, that's a continually operating reference station. It's basically a GNSS antenna that's set up a lot of times by government, universities, and sometimes even private companies do it. And it's just a GNSS antenna that's set to a very secure location, like a solid concrete brick on a roof of a building, and it runs 24 hours a day for years and years and years on end. And that's actually fed back into federal data systems that manage geodetic operations and research, and can also be used for commercial applications like us. So if a core station is within, I'd say, about roughly 12 miles of your position, you can use that as your base station in lieu of your own, but I would recommend that's only a break glass in case of emergency type thing, because you don't know what the status of a core station is. It could be malfunctioning. The operator could have, quit his job and not checked on it. There could be a data outage because of a power failure. You have no idea, and you don't ever want to hinge your work on an unknown variable like that. But we do have other options for base stations. We have the Atlantic Smart Base and the Trimble Centerpoint PPRTX. These are paid optional services. And they're still not quite as good as running your own local base, but they're still very good. Basically the way these work is that they look at all the core stations around your area and sort of interpolate what the atmospheric corrections would be. Because that's essentially what you're trying to do with a base station, is you're trying to correct for GPS biases that are introduced. Like the signal sort of gets slowed down as it goes through the ionosphere. Every clock has a slight amount of error. So, GPS satellites are basically just clocks that are just spewing clock times down to Earth constantly. And, those small, like microsecond distances between those introduce clock error. So that's why we, use base stations to correct for all those biases. Let's see. One important thing to keep in mind when you're operating a base that a lot of people get confused by is that when you go out to do a TrueView survey, and this only applies to like a fresh site that's you've never been to before, you're doing two jobs at one time. First, you need to take a minimum 2-hour static observation to get a post-process solution. So when you set up, if you set up even the most high-quality GNSS antenna, without differential corrections, it's going to be like only a meter of accuracy. You've got to sit there and observe a 2-hour static point that you send to a post-processing positioning system, and it will narrow it down to like 1 centimeter or 1 or 2 centimeters generally. So getting that known point is your first priority. You got to have that. The second priority is that base station needs to be running at all times during flight. So those are two completely separate jobs that do have a lot of overlap. So for instance, if I go out to a new site that I've never been to before, the first thing I do is pitch up my base station. Nail a solid nail into some concrete or set up some kind of stable monument of some kind and get that base station cooking to get a 2-hour observation. Preferably more. You get the best solution from about 8 hours is the point where you get diminishing returns, 2 to 8 hours. And then after I've got that base set up, I'll go ahead and set up my aircraft and start flying. Now, if I only have one flight, I'll fly the flight, pack up, and sit there and wait for those 2 hours. If I come back the next day, I'll set up my base station, fly the flight, and then break everything down. You only need to get that initial observation and post-process position the first time. Afterwards, the only requirement is that it runs during the drone flight. And I highly stress that you need to trust that position. There's USGS benchmarks scattered all throughout the United States that you can get reports for. But if you look at the date they were last checked, it might be 10 years ago and it's no good anymore. And you don't know what's happened at that site since then. Heavy machinery could have went around, tectonic activity shifts points around a few centimeters, every few years. You need to trust the point that you're using. Does all that make sense to everybody? Anybody need any clarification on that? It's a pretty important topic with these. So local base station requirements. If you are and you should be running your own local base station, at a minimum it needs to have L1 and L2 signal support. These are two different frequencies that GNSS signals send out. So they're sending it at two different frequencies. So two different frequencies are going to get altered by the atmosphere in two different ways, and it can look at both of those frequencies for the difference and help solve GPS or GNSS biases. That's absolutely required. At a minimum, you're going to want GPS and GLONASS constellations. So GPS is the US constellation, GLONASS is the Russian constellation. It's working for right now. We'll see what happens. You do want those. You could get away with only using the GPS, but you might have certain cases where it's just not enough. I had somebody the other day set up their base station only for GPS, and they had 6 satellites for most of the survey, but it dipped down to 5 at some point, and their trajectory solution was no good. So be sure to get both of those constellations. Your base station needs to be able to export RINEX format, 2.11 or later. That's just a data format for GNSS observations. I don't know of any base station that doesn't support those, but it needs to be there. The lat long and elevation, that's the known position that will be derived from your static solution. Antenna height's an important one. A lot of people these days now are using fixed height poles, just a 2-meter fixed height pole. You don't have to measure it. You always know what it is as long as your spike's not worn down. But some people still use tripods where you've got to manually set that up and level it out, and your elevation is going to be slightly different day to day. So if you don't have a fixed height pole, you need to measure the distance from the tip of your spike to the bottom of your antenna every single day to the millimeter and log that and know those things. You'll need to know the manufacturer and model of your base station. There is that is needed for certain calibrations. And they all need to be recording at a 1 Hertz interval or 1 second interval. That 1 Hertz interval is required to achieve the advertised accuracy and precision that we advertise for the TrueView system. If it's any less than that, it will interpolate the results and have degraded data quality. And while I'm talking about GNSS stuff, I should go ahead and talk about checkpoints. So a lot of people that come from the world of photogrammetry are used to the concept of a control point. And the control point will sort of augment your model. You'll fly a mission and your data will be as good as whatever the instrument is, and then you'll have control points that will augment that model to bring it up to specifications of what you need. And then you'll also have checkpoints that will independently verify the accuracy of the model that you've created. This is kind of, the TrueView systems are all what we call direct geopositioning systems. They don't need control points anymore, but they do need checkpoints. You should always lay out checkpoints to verify the accuracy of your work. And the checkpoints, like you can see on the picture, a lot of times it's just a checkerboard target or an X that you spray paint on the ground. And you'll go out there with surveying equipment like a basin rover or a total station, and you will survey and get the accurate point of these, X, Y, and Z. Most basin rover systems operate within sub-centimeter accuracy. So you're measuring these checkpoints, and then once you process your point cloud and orthomosaic from the TrueView system, you will calculate the deltas or the differences and compile statistics of the difference between these checkpoints and your data. And that's how you get your accuracy assessment. So that should always be done for all any kind of aerial mapping should have, you know, accuracy verification for it. We have this article on our website. We regularly do these articles that have special topics. You know, anytime we have customers that we get a lot of questions about a certain topic, we'll write an article for it. So this is here, and this sort of explains the difference between control and checkpoints and kind of defines some of the terms and why it's necessary. I won't go into this, but you will be getting a copy of this PowerPoint. And if you want some more clarification on that or other topics, I'd check out that link. One thing to keep in mind when you place checkpoints is make sure that they're on a flat, uniform surface. So you don't want to put it next to buildings, next to curbs, next to you know, bushy vegetation. Nice, flat, open area so that they're not obstructed. Within the manual, the hardware manual for the TrueView sensors, there is a mission checklist. And I highly recommend that you use checklists in your practices, especially when you start out, because there's so many components and so many points of failure that can trip up as you're learning this workflow. You can get these checklists from our manual, and I would also suggest that you just augment them for your own company specifications. Every company has different equipment, different requirements, safety protocols, stuff like that. So highly recommend that you compile your own checklist and make sure that you follow it. And then field checking data. I'll touch back on it again with this when we come back in, but we also have another place for articles. If you go to support.geocu.com, we have a knowledge base where a lot of the common issues that customers have and questions that we have, we compile into articles to help people out. And one of them is a pretty extensive article on field data checking. So, you know, the short answer is, you know, field operations are expensive. You got to pay for hotels, you got to pay for gas, you got to pay for travel. Per diems, you've got restrictions from weather. Some customers have temporal restrictions. We want these stockpiles scanned on this date. Or you know, there's so many considerations. So when you go out into the field and collect data, you need to be absolutely certain that you're coming back to the office with good data. So you want to go through a few data checking processes, like checking your controller box lights, inspecting cycle logs, inspecting your image quality, looking at the size of your laser.bin file, which is the LIDAR observation. And you can also just import this data set and start the first part of the processing. So the actual import process of a data set from a TrueView is really quick. You know, I'll go over it into excruciating detail, but once you get the hang of it, you just do it in like 15 minutes. So it's a good thing to just do in the field to just have some certainty about the quality of your data. So, and I will revisit this once we have our data set for today. And then that will lead into post-processing. That will be once we get back and throughout the rest of the day. Okay, so what I'm gonna do is I'm gonna throw this on the cart, and we're gonna go out the door, swing a right, and then out in the back we have our manufacturing area that you can see where we assemble all the sensors and orders and everything. And we'll go out the bay door to the back side where we've got flights.